Recording's up and going. Cool. So, electronics. So, we're talking about a little bit more about electronics. We should only have a couple more weeks of it, this week and next week on electronics. Okay, we've got a couple more weeks after this, and then we'll be into revision for you guys' capstone. So, who can tell me what we did last week? Okay, so last week we got into a little bit about capacitance. Cool. So yeah, last week we talked about capacitance, the typical ratings, microfarads, some in picofarads, which are even smaller. We talked about variable capacitors, which you can change the amount of capacitance, typically used for radio frequency applications. Then we had applications, things like electronic coupling and smoothing, contact protection. So if we've got an inductive load like a transformer or a motor, it stops the switch being damaged because all of the backwards EMF wants to go towards that capacitor, which looks like a dead short, but it isn't. Talking about radio frequency suppression and about safely discharging capacitors. So when you're discharging capacitor, always make sure you use an adequately rated resistor. Sometimes that's literally just an iron bar across the terminals, because anything greater than 5 microfarads must be provided with a discharge path, and anything greater than 5 microfarads can have quite a high peak. So we went over the formula, being capacitance equals quantity of electric charge divided by voltage. But you won't need to use this formula too much because most of the time you'll be given capacitance. Then we talked about the permittivity of the dielectric, and that little 3 symbol is what it is. Area of the plates and distance between the plates are all the things that have factors in capacitance. Cool. And then we talked about how if we have capacitors in series, we increase the actual resistance or capacitance, and then if we have them in parallel, we reduce the capacitance. Cool. So, and then we talked about the time constant, how after 1 time constant, it's 63% full charge, and then charged after 5 time constants because it slows down as it gets towards full charge. Talked a little bit about semiconductor theory, which is going to play into tonight, how a semiconductor is sometimes an insulator, sometimes a conductor, depending on the charge or voltage we apply to it. We looked a little bit at the periodic table, how all of them are in group 14. So group 14 here, these are all considered semiconductors. So you've got silicon, germanium, believe it or not, tin, lead, and don't worry about that last one. I'm pretty sure that's very hard to get. And then we looked at the difference between a P-type and an N-type, and the P-N junction, which we use to create semiconductors, including diodes, and how they work in either work in forward bias, but if you put them in reverse bias, there's very little current flow, almost none. That's a small recap on last week. So this week we'll take a look at diodes. So diodes are semiconductor components. They're made up of different combinations of P-N junctions. It's the simplest semiconductor component composed of a single P-N junction. The cathode is marked with either a white or black band or with the letter K. Letter K is used for the German spelling of cathode. So a lot of the science around electronics we get from German engineering because they were quite well equipped at one point in time before a certain mustache man showed up. So when forward biased, there is a narrow depletion layer which allows current to flow. This depletion layer causes a small volt drop. All diodes have a volt drop across them when conducting, usually around 0.6 volts. And then when reverse biased, the depletion layer is widened, blocking the flow of current. So a small leakage current of a few microamps may flow. So yeah, you've got your PN junction there, you've got anode and cathode, you've got your indicator bar there on the diode, and this is the symbol for a diode. How many of you guys have seen this symbol before? Okay. Why don't you guys give me some examples of what we can use diodes for? Rectification, yep. Any other type of uses? Cool. So here's some examples of diode packaging. So remember, current can only flow in the direction of the arrow. So we'll be looking at three types of diode: a signal diode, Zener diode, and power diodes. So a signal diode, so in forward bias, so it only allows current flow in one direction, suitable for high frequencies and suitable for low current applications. So in forward bias, the diode starts to conduct at around 0.7 volts and reaches a maximum volt drop of about 1 volt at full current. The current flow increases slowly versus the voltage is increased, but then it rises rapidly to a maximum value when the diode is fully biased. So here we can see for conduction, so forward anode voltage starts at about 0.7 and then keeps going upwards. So in reverse blocking, it can handle just past 200 volts and then breakdown and reverse breakdown or reverse conduction. So at that point, it will be no longer able to block the current flow at that high voltage. So it's good for low voltage and low current applications. So just over 200 volts, reverse breakdown, limit of the diode is reached and the current flow rapidly increases. This will destroy the diode. The diode in the circuit should be adequately rated so the breakdown voltage will never be reached. So signal diodes are used exclusively in audio FX circuits, such as guitar pedals or voice modulation equipment. The original Dalek sound was produced by a circuit known as a ring modulator, which mixed a half-wave rectified sine wave with a half-wave rectified human voice. So that's how you got the original Dalek sound. Any of you guys are Doctor Who fans out there? Any questions about the signal diode? No? Cool. So we will move on. Cool. So a Zener diode is designed to operate in reverse breakdown. So it's used for stable reference voltage and clamping. So if an excessive reverse voltage is applied to a regular diode, reverse breakdown occurs, which results in damage to the diode. Zener diodes are designed to operate continuously in reverse bias. So in reverse bias, a Zener will give an exact volt drop, which can be used to provide a reference voltage to drive a power supply or draw circuit. So Zener diode can also be used to clamp a signal voltage, providing an absolute maximum voltage input to a microcontroller. So which prevents damage if the line is brought to excessive voltage, so component failure or induced EMF. The Zener diodes come with a maximum wattage rating, which must not be exceeded. So we break that down. So it's always in reverse bias. So they're designed to operate continuously in that state. So it'll give an exact voltage drop, which can be used to provide a reference to drive a power supply. We look there at the curve. So negative 2 volts, it starts to conduct. And then at negative 6 volts, it starts to conduct. At negative 8 volts, it starts to conduct. Who can think of a purpose for this type of diode? So what would you use it for? Explain how you would use it. Yep, we can use it for protection. Basically, we can use it to basically create a signal so that if the voltage goes the other way or it goes into incorrect polarity, it will cause a signal to go back to the protection device or to a relay and turn off the supply. That's basically the use for a Zener diode. Cool. And then power diodes. So power diodes are quite easy to explain. So they're similar to small signal diodes, but designed to handle much higher currents and voltages. So current ratings from a few amps to several thousand amps are common, as are voltage ratings from 100 volts to several kV. So it's used for rectification, AC to DC conversion, and the volt drop is similar to a signal diode, around 0.7 volts. So where would you use a power diode? Do you think of any everyday applications for a power diode? Yep, for chargers. Anything else? That's fine, Oliver. You've checked in, so I'll mark you as present. And if you want to watch the recording later, that's fine. Anyone else think of an example of how we'd use a power diode? So if we think about modern electronics, a lot of the appliances we use today come with power bricks that are essentially AC to DC rectification and step-down transformers, so a driver. So we think about in terms of a driver being a rectification and step-down transformer. What would we then use a power diode in conjunction with this piece of equipment? And just remember, guys, your participation in the chat is generally how we do attendance. So if you're logged into the call but don't participate, it's basically the same as not attending. So yeah, we've got chargers, but there are a few other devices. Throw them out there. There's a pretty big one that runs between the North and South Island. Yep. So yeah, there's pretty large power diodes for the HVDC mainline, where it gets converted from DC from AC to DC when it goes under the Cook Strait. So the HVDC link actually only technically the power lines run from Benmore to the Hayward substation, but the actual only DC part is the underwater cables. So it gets rectified and then inverted at each end of the actual underwater part. Pretty sure it does. Cool. So yeah, you've got the HVDC link. You've got all of your TVs to ensure that polarity doesn't get put backwards just in case. So I think everything from your TVs to your laptops to your gaming devices, anything electronic we use every day more than likely has a power diode in it. There was one instant where a whole bunch of TVs got tested but with 500 volts DC with an insulation resistance test, and this was too much for the power diodes and the TVs. So all the power diodes and the TVs went pop, 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 and all the TVs got written off and replaced under insurance. But someone who knew a little bit about electronics opened up the TV, found the power diodes, found it was fucked, replaced the power diodes, and then they got about 5 or 6 new TVs out of it. You can ask DK about it if you are at block course. He'll tell you the story. I don't know the full details, but he loves to tell it every year 3 block course. Cool. So moving on. And then, of course, we have our LEDs. Sorry, I'm just going to adjust the screen a little bit. That's better. Cool. So basically, a light emitting diode, a diode that emits light when biased. So when it's in forward bias, it emits light. When it's in reverse bias, most of the time it does not like it and will blow up. So it's low consumption. It's a small 5 millimeter LED, draws only a few milliwatts. So it's small size, suits construction on PCBs and allows an array of LEDs to be constructed for signage. That's fast switching infrared LEDs on TV remotes, transmit codes reliably at several kilohertz. Physically robust, the LED is encased in resin, protecting it from impact and moisture. It's long lasting with a well-designed driver circuit. An LED can last upwards of 50,000 hours. So it must supply more than biased voltage, must limit current with resistor. So small size, fast switching, physically robust, long lasting. It's why we use them for lighting in most applications. Who can give me a reason why we might use LEDs versus fluorescent lights in particular installations? Yep, running costs. Can anyone think of a different reason? Heat, yeah, that's a good one. Low voltage, yep. Safer. There's a safety precaution as well. Just trying to remember if you guys remember about it. Yeah, that's a good one, actually. That's another one. So who's heard of the stroboscopic effect? Okay, cool. So the stroboscopic effect is basically the fluorescent light tubes will flicker at a rate of about 60 hertz, or I think it's 50 hertz because of the supply voltage fluctuating on AC. So these fluorescent lights will flicker 50 times a second. But what else is dependent on the frequency that we use? So we've talked about something last term, which is based on frequency. So when we talked about motors last term, speed is based on frequency. So if we've got a supply frequency of 50 hertz and we've got a light that is flickering at 50 hertz, what possible safety implications could that mean if it's strobing at 50 times a second? Good guess. So basically, with the 50 hertz flicker and the machine rotating based on the 50 hertz frequency, a object in, say, a lathe or a rotor on a motor may appear, instead of rotating, to be stationary. So that it looks like the machine's not spinning when in reality it is. So that means that potentially someone could think or assume that the machine is not operating and then be less cautious around it. So there's a potential for the danger of the machine, the spinning machine, accidentally sticking your hand in it, things like that. So it presents a safety issue. So the options to fix that are having two fluorescent lights next to the machine, one on red phase, one on blue phase or white phase. So the strobing is at a different rate. So it appears that there's more of a constant light, or we can replace the fluorescent light with an LED, which, because it runs on DC, is a constant light source. So write it down somewhere, the stroboscopic effect. It may come up in the capstone as a safety question. It's come up before, I think. Yeah, make a note of that, the stroboscopic effect. One other thing to do with fluorescent lights and education facilities is that because that flicker is just beyond what the human eye can perceive, it actually can cause migraine. So if you guys went to a high school that had fluorescent lights in the classroom, as the day wore on, you'd probably get a bit of a headache because of the fluorescent lighting. So a lot of places have switched to LED, and now the Ministry of Education has rules about the types of lights, how much light, the color of light that is required for the classrooms, depending on what type of classroom it is. So if you guys ever work in a school, you'll know that you have to pay close attention to the lighting, or someone will have designed the lighting for you to ensure that it meets those requirements. Yeah, and usually that'll be in the form of LED pan fittings. Cool. So some terms. So forward volt drop. So this is the volt drop in forward bias. So silicon typically is 0.7, germanium 0.3. LED volt drop varies with color, and it's around 3.2 volts for white or blue and 2 volts for red. Again, this is just kind of stuff you need to be aware of. I'll be honest, when I did my capstone back in the day, we got asked about we'll talk about it soon, a full wave bridge rectifier, and that's about it. Yeah. Forward resistance, so we can use an ohm meter. It has a fairly low test current and will not be able to bias the diode to properly measure its internal resistance. Therefore, it will read quite high, between 100 to 1,000 ohms. It's above 1 kilo ohm, indicates a faulty diode. So when forward biased, a diode's resistance becomes very low, typically less than an ohm, maximum, average. So I'll show you guys some diodes in a little bit after we get through the slides and how to test them. Cool. So your maximum average forward current. So the maximum forward current that the diode can handle continuously. So the diode can be subject to peak forward current higher than this value, but only for brief periods. So basically it's don't go past this current, otherwise you may damage the diode. Cool. Junction temperature. So it's the temperature range the diode will operate normally within, typically anywhere between negative 55 to 150 degrees C. So you're not likely to go past this unless you pile on the insulation inside of a roof space and sandwich the driver inside and then maybe also put it inside a grow room. I'm not saying to do that. Cool. So higher temperatures can damage the diode. Larger power diodes are built with provisions for heat sinking. And obviously you're not going to get below negative 55 degrees unless you're working inside of a commercial freezer. But then there are specific lighting requirements for freezers, usually totally enclosed to prevent that kind of thing and prevent the buildup of moisture. And then you got your peak inverse voltage. So it's the maximum reverse voltage that it can withstand without damage. So good practice is to pick a diode with double the required peak inverse voltage for the application. So if it's a 24 volt supply, maybe go with one that has at least 48 volts of inverse voltage. So power dissipation. So as the diode has a volt drop and allows current to flow, there will be power dissipated. If this power causes the temperature to rise higher than the junction temperature, the diode will be destroyed. So similar to a resistor, how much power it can safely dissipate. Cool, leakage current. So the current that will flow in reverse bias, it's typically tiny, a few microamps, and is small enough to be ignored in most applications. But if this leakage current exceeds 50 microamps, this is indicating the diode is starting to fail. VRRM. So this is a bit of a strange one. So it's the maximum repetitive instantaneous reverse voltage value the diode can be subjected to without damage. So the maximum peak voltage of the AC supply, for example. So maximum repetitive instantaneous reverse voltage. So if we think about the AC supply, our maximum voltage is around 325 volts. 230 is just our RMS. So we have to make sure that the VRRM for rectification is higher, or maybe, yeah, especially if we're using, even if we're using transformer, is higher than 230 volts if it's being subjected to AC, just so that way it won't get damaged by the instantaneous reverse voltage that could be applied to it. Reverse breakdown is when reverse voltage is too high, causing a breakdown of the PN junction. Once this occurs, an avalanche effect results in current flow rapidly increasing until full reverse current is reached. So basically, it's the maximum reverse breakdown is the point at which it will break down and allow current to flow freely in reverse. The Zener point, so the reverse voltage drop of a Zener diode, this voltage is usually set by the manufacturer. So those are just some terms to be aware of. They are in the learning resource. So yeah, if you guys haven't looked, every time you open a section of your Moodle, I'm sure you guys are familiar with it, there is a PDF that contains all the possible information you could need to do any of the assessments. So if you're struggling with an assessment, try opening up that PDF and having a look through the using the find function. And if it's worded a little bit differently, feel free to email me. I'm more than happy to help you guys with questions. Just I won't give you the exact answer, just point you in the right direction. Cool. So this is an example of a half wave rectifier. So basically it has a diode on one arm. So basically it will only rectify half of the AC waveform. So it wastes half of the AC wave as it only conducts half the cycle. The output is extremely lumpy and in most cases must be filtered with capacitors before use. It's obviously not very useful, kind of a waste of power, waste of heat, basically power wasted to heat. It's the most simple form of rectifier from AC to DC. Cool. This is what we call a full wave center tapped rectifier. So by using a center tap common terminal, full wave rectified DC can be produced by using two diodes. The disadvantage to this, it requires a more expensive center tapped transformer. So you wouldn't normally see these. These are what they came up with before they came up with a full wave bridge rectifier. So it produces a full wave rectified DC. It requires a smaller and cheaper transformer than the center tapped rectifier, as only one secondary winding of the same size can provide full output current. But in your drivers and the drivers for your LEDs, you'll have a transformer that is usually stepped down from 230 to 12 volts. You will also have other electronic equipment to ensure that the voltage never reaches above 12 volts. Cool. So we take this circuit. So we'll look at, so the first time we get through half of the AC waveform, current is flowing in this direction. So it will come down here, it will get to this point here. It's got two options, tries to go this way, rejected. And then it comes down here and flows down here, but can't go this way, it gets rejected, then comes down here to the load, then it comes out of the load to this point here, and then it can either go this way, but it wants to go back to this point, so it's going to come down this way through this diode and back to the transformer. Does that make sense to you guys? Wait, and just so we can go over it again. Cool. So you may have to draw this. So now the current is flowing this way. So it's going to come along this path here. But again, tries to go this way, rejected. Comes this way, tries to go this way, gets rejected again, comes down to here. Now it knows it wants to come this way. So it's going to follow the output again, but instead of going down, it'll go this way and connect up with the other end. So this is how the current flows in both directions for the full wave bridge rectifier. So this is the most common type of rectifier circuit you'll come across. Usually it won't have a straight transformer like this. It'll normally be like 230 to 24 or 12 volt. Based just depends on the requirements of the load or the circuit. So yeah, this usually more often than not comes up in the capstone. Not 100% sure on the digital ones, but I think last 10 paper capstones from back in the day had a question about a full wave bridge rectifier, just because it is the most common type of rectifier circuit you'll come across. So yeah, it produces a full wave rectified DC. It's smaller and cheaper transformer, but it still requires smoothing. So usually it would be achieved by a capacitor and other smoothing devices. Cool. So a freewheeling diode. So this is also called a flywheel diode or flyback diode. So it projects a transistor from a back EMF. So like we talked about before, back EMF or electromotive force is a voltage spike generated when switching off inductive loads. So who can give me some examples of inductive loads? Yeah, motor. Yeah, fan. Fans have inductive coils in them. Yep, transformer. So one of the other options would be a relay coil or a contactor coil, because they are just basically one big F-off magnet. Cool. These spikes can damage transistors. Spike occurs because the inductive load's magnetic field collapses and induces a high voltage in the circuit. High voltage can exceed the transistor's voltage rating, leading to its destruction. So to mitigate this, we can use a diode, so a flyback or freewheeling diode, connected either across the transistor output, allowing current to flow safely when the load is switched off. Or another method is to use a resistor in series with the transistor and a flywheel diode across the relay coil to limit the current flow. Cool. So it's an arc suppression circuit. So it's the same concept as a freewheeling diode. So on a large DC load, a diode can be used to prevent arcs causing damage to a switch. So it's to protect the switch. Cool. So testing semiconductor diodes. So diodes fail if their maximum ratings are exceeded, say the forward current, junction temperature, or reverse voltage. So diode faults include an open junction, shorted junction, or a leaky junction. So insulation resistance test may destroy diodes like the TVs I was talking about. So insulation resistance test should be performed by bridging P&N and testing to earth, so phase and neutral to earth, so diodes do not receive 500 volts test voltage across their terminals. So when you're testing your circuits that contain LED lights, you can twist the phase and neutral conductors together, put one of the test probes onto that, and then one of the test probes onto the earth for the circuit, and then you can test. So most of your electronic equipment will have a transformer in it. What happens, do you think, if we put an equal amount of voltage and current flow down both sides of a transformer? So basically, there would be no magnetic field created because the currents would flow into each other inside the transformer coil and negate each other. Yeah, and the voltages would hit each side of the diode and basically not conduct because they're basically hitting each other in the head. Cool. So that's the PowerPoint. So now, hopefully this works. Hopefully this works. I have a document camera and I'm trying to connect it to the room. Right. My document camera is deciding not to want to connect. So I Okay, so here we have a box with some diodes in them. And it's not very good quality. Sorry, document camera's not really working. Maybe if I go. A little light on the subject. Yeah, you can see it's a box with some diodes in them. Cool. There. Got some diodes. Here I have my multimeter. So testing diodes, move to the diode function. So give me 1 second. So if we note here on the diodes, we have, get it real close, you can kind of see, you have a colored strip on the top there, or the top as you can see it. So we know from what we talked about before, the strip is the cathode. So if I take my multimeter, put it in, I have nothing at the moment. But if I take my probes and I reverse them, I believe I'm getting a reading. So I'm getting 0.54 volts DC. So that's giving me a volt drop. If I then move to the next diode, so I believe that's a power diode. So this is a Zener diode. So I'm getting about 0.7 of a volt drop. And then I believe the last one is a signal diode. I'm getting a 0.57 volt drop. So that's how we can test the diode. So we can check it in forward bias. And then when we go and check it in reverse bias, we get nothing because we know in reverse bias it will not connect. I'm hoping everyone was able to see that. Oh, it went back to the. All right, so that is your basic testing of a diode. So if you can do that basic testing of the diode, then you can fix things like the signal diodes in your power diodes in your TV. Okay. So cool. So name the 3 elements used in the doping of N-type semiconductors. So look back at your notes. Feel free to open your PDFs, but find me 3 elements used in the doping of N-type semiconductors. You guys look that up. I just got to quickly pop out of the room. I'll be back. All right, has anyone got some answers for me for question 1? Okay, so silicon is the actual semiconductor material. We're looking for the doping agents. So the first example I'll give you guys. So arsenic. Arsenic's one of them. Yep. Phosphorus, that's a good one. Now I'm just checking your spelling versus mine. Yep. Someone else give me another one. Yep. Nice one, Spencer. Yep. Yep. So that's 3. That's good. So what about P-type? Definitely boron. I don't think we'd use, yeah, gallium and indium, yeah. So I would be a little bit leaning away from saying aluminium just because it is a fairly conductive metal. Yeah, cool. So what is the term best to describe the lack of an electron in a semiconductor? It's one word. What term is used to describe a lack of electron in semiconductor? Yep, holes. Good one, guys. Cool. So when a diode is conducting, it's said to be in what? So when it's conducting, it's in one state. When it's not conducting, it's in the other. Yep, forward bias. Cool. And I'll just leave those up there for a sec. Bias or biased. I think it's just bias. Cool. So I'll leave that there for a minute, just for people who are watching this online, just to get the answers. Cool. So if we move down sheet a little bit, let me grab my mouse. Oop. Cool. To give me 3 types of transistors. Feel free to just Google these. Cool. So I will give you one. So bipolar junction transistors or BJTs. I will accept the 3-letter answer. Field effect, yeah, FETs. So field effect transistors. Yep. NPNs. Yep. That's a good one. So an NPN is 2 N types sandwiching a P type, and then we also have PNPs as well. Yep. So there we go. That's 4 examples instead of 3. Cool. So we haven't covered this, but have a look up for it. How does a Schottky diode differ from a power diode? Okay, all good, Alex. So I will answer this one. So basically, Schottky diodes have a basically they have a lower voltage drop and faster switching drop. So lower volt drop, faster. Oh, that looks horrible. Switching. So they're very similar, but obviously power, yeah, fast switching. So power diodes are used for higher power applications, whereas Schottky diodes are used for a lower volt drop, low power circuits that require faster switching. So draw a simple circuit diagram using a resistor. Okay, cool. So don't worry about this question simply because you guys don't have the draw function on the Teams. It is an option for a different version of Teams. Sorry, that disappeared again. Okay, we'll call it there, guys. So good effort tonight. So this is our 3rd night class of the term. Oh, this, and so we have, after this, we have 6 weeks of term left. That 6th week being when you have your capstone. So what I will do now is because we've officially finished. Stop recording.